Hello everybody and welcome to another video lesson. In this video lesson, we're going to break down what algorithm efficiency means, what algorithm complexity means. We're going to introduce big O notation and show you how to calculate big O for some simple coding examples. So to start, we'll discuss what is algorithm efficiency. So algorithm efficiency explains the big picture. It describes how well an algorithm uses computer resources, especially in terms of time and memory, as the size of its input grows. Efficiency is important because in the real world, we often deal with huge data sets. Think millions of users, think thousands of transactions. An algorithm that works fine on small inputs might slow down drastically. It might even crash the program when you scale up. And that's why it is crucial to understand how an algorithm's performance grows and whether it can actually handle large inputs efficiently. We measure efficiency to help us choose the right algorithm for the job, not that one that not only works, but one that works well under pressure and as input size increases. So, what is algorithm complexity? Algorithm complexity refers to how an algorithm's performance, in terms of time, how long it takes to run, and space, how much memory it uses, changes as the input size increases or grows. In other words, it answers the question, well, what happens when we double or triple or drastically increase the amount of data the algorithm has to handle? And when we talk about algorithm complexity, there's a focus on growth. We're not usually concerned with how fast a program runs on a small input like 5 or 10 things. We're more interested in how the algorithm scales, how much longer or more memory it will need when input sizes reach hundreds, thousands, millions. And it matters because knowing algorithm complexity will help you choose the right tool for the job. It helps you avoid inefficient solutions that might look okay at first, but fail when you try to scale up. And it's also a language and hardware independent way to talk about algorithm performance. Okay. So what is big O notation? Big O notation is a mathematical way of describing how the runtime of an algorithm grows with input size. It gives us a worst case or upper bound estimate on the number of steps that an algorithm will take as input increases. And we usually represent the size of the input as the variable n. It's like saying no matter what happens, the algorithm definitely won't take longer than this. Big O, to summarize, Big O is a mathematical way to describe how the runtime or the space requirements of an algorithm grow as input size increases. And it expresses the upper bound of an algorithm's growth rate. Again, helping us understand its worst case performance as the input scales up. And why do we use big O? Where does that even come from? Well, growth rate functions describe how an algorithm's runtime or memory usage increases as the input size growth using abstract math functions like O of n or O log n. It makes it easier to compare algorithms without consideration of hardware, programming language, other details, and it helps us generalize and predict algorithm performance. They also allow us to, the functions specifically also allow us to compare algorithms that solve the same problem. So you can choose which one works best for the input that you have. It helps you choose the most efficient algorithm. It helps us identify bottlenecks and design more scalable software systems. So again, the growth rate functions help us predict performance in a way that is not tied to any specific hardware, any specific programming language, and they make it easy for us to compare algorithms together that might solve the same problem, you could just pick the one that works the best. And then here I have a chart of some of the common growth rate functions. And the x-axis n represents the size of the input, and the y-axis represents the value of the growth rate function at that input. So growth rate functions increase, as input increases, the growth rate will begin to slow down, but how it slows is different with every function. So we look at an example like log2 of n. This is growing logarithmically. It's growing rather slowly. And then you see an example that is exponential up here, 2 to the n. This is growing super fast. It is going to get out of hand very quickly. And in the next slide, I will go over the specifics of some of these growth rate functions. So here are some common growth rate functions that we use in big O notation. So constant time, depicted here as O of just the number 1, represents constant time, the algorithm takes the same amount of time no matter how large the input is. For example, it's like an example would be accessing an array element, so by index. So let's say you're accessing the third element in an array. That could be done in constant time. We have logarithmic time. The algorithm's performance increases slowly, even as the input grows. And an example of this would be binary search, because each step cuts the problem in half, so it grows pretty slowly. And then you have linear time, represented as O of n. The algorithm's time grows 1-to-1 with input size. If the input doubles, so too does the time. So I like to think of this one as 1-to-1. And this would be, an example of this would be like looping through an array one time. You have to do this n times for every element. We also have linear-rhythmic time, which grows a bit faster than linear, but slower than quadratic. And it is common in efficient sorting algorithms like merge sort or quick sort. And then you really kind of start to slow down here with quadratic time. Time grows with the square of the input size. If the input doubles, the time increases fourfold. And you're going to see nested loops as a pretty common example of quadratic time. Nested loops over an array like selection sort or bubble sort or something. You also have exponential time, which we saw in the chart. They wrote as the most, it doesn't scale well. Time doubles with each added input element and becomes impractical very quickly. And an example of this would be like solving the traveling salesman problem by brute force. And then finally, not pictured in the chart, is factorial time. Performance worsens dramatically as input increases. So an example of something running in factorial time is like solving the 8 queens problem with all possible arrangements. Super impractical, not something that you would want to do at scale. All right, let's go to the next slide. All right, so how to calculate big O. So there's 3 rules that we're going to go over. They are also the 3 rules found in your textbook. So if you wanted a little bit more information about it, you can always read the textbook. I think the textbook is a little bit more mathy in how it explains things. And I know that that's a way that some of you communicate best in, and that might work for you. But I'm going to explain it a little like with more simplistic terms than that so that we could get the general idea. So you can ignore low order terms in an algorithm's growth function rate. And we ignore low order terms in big O notation because big O is all about understanding how an algorithm behaves as the input size becomes very large and approaches infinity. When that happens, high order terms dominate the growth. And so you'd have smaller terms like this +4 in this example, for example, this plus 4, this plus 3, this times n, they have minimal impact on the performance when n is very large. We care most about the dominant term, which defines the scaling behavior. So in this example here, O of n to the third plus 4 times n to the n squared plus 3 times n, we can drop the smaller terms and we keep the largest term, O(n) cube. And so if you were going to write this in big O, we would just say big O of n cubed. And the next rule, we ignore multiplicative. You can ignore a multiplicative constant in the high order term of an algorithm's growth rate function, and we ignore multiplicative constants in the high order terms of an algorithm's growth rate function because big O is meant to describe trends, not precise measurements like constants. Constants could vary with hardware, for example, vary with compilers, vary with optimizations. And they don't impact the fundamental nature of an algorithm's performance as n approaches infinity. So we can actually drop constants. You can ignore multiplicative constants in the higher order term. And then finally, we can combine growth rate functions because real-world algorithms often have multiple parts, each contributing differently to the overall performance of the program. By combining their growth rates, we get a clearer picture of how the entire algorithm scales. We have an example here where we have O of n squared plus O of n, and we can combine that to O of n squared plus n, and then we can actually drop the plus n term because we're only interested in the slowest growing part. Big O is an upper bound, remember that. Our only interest is in the slowest growing part, the part that takes the most time as input grows. And combining lets us model complex behaviors more realistically than to just simplify them for clarity. All right, so now we're going to go over some examples and we're going to use some of the rules and some of the information from the previous slides. So in example 1, calculate big O for the piece of code. We have a for loop, int I equals 0, I less than n, I plus plus, and then during that loop, we're going to output I to the console, and that's it. And so to evaluate this, we want to identify how many times this is going to happen. Right? And so we're going to start from 0 and we're going to go all the way to n. So this is going to happen n times. We evaluate this piece of code to be big O of n. And the loop, like I've mentioned before, runs n times. Each time, this is important too, it does a constant amount of work, which is this outputting of I. It's just a print statement. So with this example, the complexity is big O of n. And then in our next example, we have a nested loop. So we have for int I equals 0, I less than n, I plus plus, and then nested within that is another for loop, int j equals 0, j less than n, j plus plus. And then we output both I and then a comma and then j. So I want you to look carefully here as well. Notice that I and j are independent. Int I starts from 0 and j starts from 0. They both go to n. They are independent of each other. They're both simply going to n. That is important. So this piece of code evaluates to big O of n squared. And that's because the loop is nested. So for every I, we loop over j from 0 to n for both of them, and they are not dependent on each other. And this is n times n operations. So the n here multiplied by the n here gives us how many times this is going to run. And that n times n is also written as n squared, which is why this is big O of n. The next example is a little more difficult. So we have int I equals 1. And we have a while loop that says while I is less than n. I times equals 2. So each time through the loop, I is going to double. And this is going to actually provide us with something that's looping log base 2 n times. So this is just big O of log n. And there's a general rule when we talk about this type of behavior. If you have this kind of loop, then the loop runs about log c of n times. And in big O, we drop the base. So the base is this part right here, log c, this little part here. In the previous example, it was 2, log 2 of n, and we dropped it in that example. But in the general rule, you drop the base, and so the answer is simply O log n. And that's generally how these ones work. So since the loop runs log 2 n times, we say the time complexity is big O of log n logarithmic time. In general, any loop where a variable is multiplied by a constant, like I times equals 2, and each iteration results in logarithmic time complexity. And this is because the number of iterations grows much more slowly than the size of the input. And so you could use this rule. But a couple considerations: if c is 1, then the loop could run forever. If c is less than 1, the loop might never progress. And if you're dividing, like let's say you have I divides equals 2 starting from n, it's still going to be logarithmic, just counting down instead of up. So this one is actually kind of like a general rule that I wanted to bring up here. Okay. And that is going to conclude the presentation about big O notation and algorithm efficiency and algorithm complexity. If you have any questions, let me know. And I hope you all have a wonderful rest of your week.